Okay, we spent like all that time yesterday going over the instructions that we were going to include in the system. And I made a big point that what these instructions are is entirely up to us. How they do what they do is entirely up to us. And like what exactly, like the nuance of what they mean is up to us, right? Like I could have always output the value from register A or from a specific memory address. I could do add and always store it in A, or maybe do a specific memory address. We did it one way here, but that's not to say that this is the right way, the better way, or anything. It's just a way, all right? Also, the order of these things here, like the fact that load A from RAM is 0001 is not really that meaningful, okay? The order is effectively arbitrary. It's not arbitrary, but the order really isn't important here. I ordered these things like logically, where I was like, okay, load RAM, load direct, load RAM, load direct, save, like loading, saving, arithmetic. Like, so I kind of grouped them, but the fact that it's 0001 means that doesn't really hold any significance. The one exception, I guess, where like there is some reason is that 0 is no op, because 0 means nothing, no op means nothing. So like there was a little method to the madness there, but all these other ones don't really matter. And I don't know, I guess I liked halt being at the end, but it didn't really matter. Even no op being 0 doesn't really matter, but that's the one that I think there's the biggest motivation for. Like 0, it's 0. The instruction is 0000, it's nothing, it's nothing, it's nothing. That's basically it. Did anyone have any questions? And did anyone kind of think about this? I hope you did. I know you think about this class in your free time, right? So I hope you spent some time thinking about this particular question. All right, so we've established that instructions, you know, they have operands and operators, which are just those like bit patterns, right? We know that they get fetched, which take a couple of steps. And we know we need to like put it into that specialized hardware, that instruction register, for it's starting to like decode it. But we still don't really have the way for the system to manipulate its own control logic. We can control the control logic. Remember, imagine we had that system up. I put all the control signals down here, right? We controlled it. And we have a way to get the instruction and isolate it from everything. And it's like ready to go, but we still haven't connected those dots. We haven't connected the instruction to the systematic manipulation of the control signals to do the computation automatically. So we still need a way to physically, the system know how to like physically perform an instruction. When I say physically, I know it's in a simulator, but like literally they think of the physical connection. We need to connect those dots. We need to connect the instructions somehow to the control signals that go activate and deactivate physically the portions of the system. We could have built this. This is a simulator. If you've been to my office, you see that thing behind me on a breadboard, like you just saw the other day. Like it is the computer, but I built it physically on a breadboard. So like the computation is physically happening, like actually. I know we are used to working at such a high level when we are writing code, but like signals and crap and transistors, all that stuff is happening physically. So this is being done physically in the simulator. So we talked about the instruction register. And like we talked right here, this will store the instruction, but the instruction is made up of the operator and operand. The operand, the least significant 4 bits, is what can go back out to the bus. It gets padded with the zeros. So we get 0, 0, 0, 0, whatever, 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 goes back on the bus, where the whatevers are the operand. The operator, though, these 4 bits are hanging out right here, and they need to be processed in some way. But we also saw that big thing that, like, look, we can't just use a lookup table, like a static lookup table, to say, take this instruction and do load A, because load A takes several steps, notwithstanding the whole fetch cycle as well. So, like, we can't just say, take this instruction, oh, go do that to the control signal, because we have multiple steps. But we can, with a stupid little trick. A very stupid but clever trick. I know, right? Stupid but clever. So consider that We have the operator specify the instruction to be executed. The most significant 4 bits. The operand goes back out. As previously discussed, each instruction requires some number of steps. Like load A required output the operand from the instruction register and put it into the address register. And then output the value from the specified RAM address to the A register, right? Load A took 2 steps, plus the additional 2 steps of fetch that we had to get beforehand, so 4 steps. Long story short, no matter the instruction we're going to do, we need some number of steps. And we call those steps like those microcodes. Microcode steps, whatever, right? But the microcodes are like the sub-steps to do any particular instruction. No matter what, even when doing a no-op, we need to take several steps because we need to fetch no-ops before we know it's a no-op. So we need a microcode counter. We need another counter. It won't be a program counter. It'll be a counter though, but its purpose is to keep track of what microcode step we're on. But it's still going to be just a counter. Now, in the digital simulator, you can go and load up a counter. There's like a built-in component counter, but there's actually 2 different counters. One is more designed to be like a program counter where you can load in states and whatnot. Another one is just a counter that just counts, right? So a simpler version. So although it's going to be a counter, it will be a different type of counter than the program counter, but the whole counting feature of it is the same. It can count. It's just we don't load data into it. It'll just count forever. So the operator can be used to specify the steps to be executed in order to perform the instruction. The operator would manipulate the control signals for the system. So we need a way to do this, basically. We have the operator, and we need that operator to tell the system the control signals to manipulate. But again, each operator, each instruction takes multiple control signals. So we need to like change the control signals actually a few times for each operator. Load A, I need to fetch part 1, fetch part 2, instruction to address, RAM to A, right? So somehow that one operator needs to mean 4 different things. However, there's a problem with the idea since instructions take several steps, the microcodes. So consider the below table of the 4 microcode steps to load data from RAM into register A. I'm using that as an example, that particular instruction as an example. I've used it several times before, but hopefully you get that I'm just using it as an example. So what are the steps? So address in, instruction, address in, program counter out, RAM out, program counter enable, and instruction in. That's fetch. And then address in, instruction out, RAM out, A in. The 4 steps. So somehow I need to say instruction 0001, or pardon me, instruction is the operator in operand. I keep saying instruction, really I mean the operator. The operator 0001 means this, 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 and this. First we have to do this, then we do this, then we do this, then we do this, then we're done. Of the 13 instructions we have, one instruction, the no-op, takes 2 steps. Or it requires 2 steps, fetch only. We gotta fetch it. Whether we like it or not, we have to fetch an instruction before we even know it's a no-op. 6 of the instructions take 3 steps, and another 6 instructions take 4 steps in total. If we go back and look at how we talked about it, the number of steps that would be required for each of these instructions that we want to have. I guess technically 4 take 2 steps because there's 4 no-ops technically, but only one of them we really cared about. The three blank instructions I left as no-ops, but they really are just like whatever. So for simplicity and consistency, consider each instruction as a group of 4 steps. So below we have a table of the microcode steps for the first 3 instructions that we talked about. No-op, load A from RAM, load A direct. What would they look like? Well, if the operator is 0000 and we're on microcode step 0, we want to program counter out to the address register. And then if we have the operator this 1, so think of these as 2 separate things. Operator microcode step. If this is the operator and this is the step, do that, do that, do that, do that. Now, no op, it's do nothing, do nothing. We just waste clock cycles. We can change the system such that you can end things early, but we're not going to do that. Never mind. If we see the instruction 0, 0, or the operators 0, 0, 0, 1, and we are on microcode step 0, fetch part A, fetch part B, instruction to address, RAM to A. Do you kind of see how like the bit patterns here? In fact, I have a question for you. Like, if I had the number, imagine I had the 6-bit number, 000111, and I added 1 to it. What would the number become? Come on. Maybe hopefully this is because the question was unclear. Let's just say I had the number 111, and you add 1 to 111. What do you get? You get 1000. Oh, wait, this is just... Look, we can actually think in the same way that we kind of did this with the... We did this with a very similar thing. Okay. We have an operator, but we also have other information we need to tell me the specific step. The operator gives me to a block of some instructions. The counter gives me a specific instruction within that block. Do you see what I mean? Really, I have a 6-bit pattern, but 4 of the bits means what operator, and 2 of the bits mean which step for that operator. 6 bits can map to every individual step for the 16 operators we have. 13 plus the 3 blanks. Is it clear? I hope this is clear. But it really is 2 different pieces of information. It is, what's the operator? What step am I on? But we can kind of think of it as one group of 6 bits, but really it's 2 things with different meaning. In the same way that the output register, that 1 bit, that sign bit, we had 9 bits of information to tell us what number to output, but that most significant bit had a different meaning. It told us which block of 256 numbers to go to, right? Tell you what's the bit pattern if it was signed or unsigned. Yeah? Yeah. So each operator specifies a grouping of microcodes. There are 16 groups of 4 microcodes. 4 microcodes per each group 1 instruction, 4 instructions, right? So each microcode can be identified by the microcode step count. So we're going to use another counter to keep track of which step of which instruction or operator we're doing. Consider the operand and microcode step together. There's a unique identifier for each instruction's microcode, right? So what is 16 times 4? 64, right? So there's 64, and hopefully 2 to the power of 6 is 64, right? So we have 64 unique microcode steps, but we can break those down into 16 groups of 4, right? Right? Logically, that's how we can think about it. Therefore, given a mechanism to keep track of the microcode step, a counter, a lookup table can still be used. The problem before is I just used the operand. The operand, best it could do is tell me which group of 4 I need. With 2 additional bits, I can tell you which exact instruction to run in that microcode. Or for that instruction, I mean. Is this clear? Make sure this is clear. This right here, by the way, this isn't the final part of the course, but connecting the instruction to how it controls the control logic is probably the big thing this semester. So we are in the thick of covering the big topic. So if you're just like I kind of get it, I kind of want you to get it a little bit more than that, So I want to make sure you're all following along because this is big. So given a mechanism to keep track of the microcode step, a lookup table may still be used. Map the operand and the 2-bit microcode counter step to the control logic for the specific microcode step, right? If I saw 000110, I would do instruction register out, address register in, and all of the signals would be 0. That's that microcode step, the patterns for the control logic, the control signals. So fortunately, there's a simple way to keep track of a microcode step, a counter, like a program counter. This counter will be referred to as the microcode counter. So here we go. Here's what I'm going to do. So I've taken the instruction register and I added a part to it. I took the operand, split it into the 4 signals, and put it into a 6-bit, 6-input lookup table. So these 4 right here, this one, this one, this one, and this one, those are the 4 signals for the operator. And then these 2 signals here are from this program counter, or not program counter, just a counter. It's just a counter. You'll know it's a much simpler counter because it has no way to like load data in or whatnot. All it has is a clock, I guess an overflow. We don't care about the overflow. Enable, we always want it to be enabled. We don't need to control when this counter is or is not enabled. We want it to pulse every clock cycle, right? So it's neat. The clock, the program counter doesn't increment every clock cycle, but the microcode counter does. Because each microcode will have to happen at each clock cycle. So that's kind of neat. And then it's got this clear, it resets it when it's 0. This could be handy. I'll come back to this idea shortly, but you have a way to reset it. So let's say this counter, if you right click on it, it would be a 2-bit counter, right? So it could only ever count 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. But like, you know how, I'll give you a spoiler. We're not doing this. We could. It really wouldn't be very hard to implement this. But like, you know how like some of those, like load direct, actually only takes 3 clock cycles, and we waste 1, right? The load direct is fetch part A, fetch part B, so 2, and then output from the instruction register, the operand, the data, into the A register. And then there's a 4th clock cycle where we do nothing, because each instruction is going to take 4 steps no matter what. So in that instruction in load direct, we're wasting a clock cycle. Nothing gets done. So what you could do is you could end it early. You can reset it such that it would like skip that last unused one. For our purposes, we're really not going to be able to gain much utility out of it. But if you had microcode steps, like the fact that our instructions can take a maximum of 4 microcodes was our design. We could have more sophisticated instructions take more than 4 microcode steps. So if you wanted it to count like to 5 or something, we'd need a way to like reset it. In fact, we'd really need a way to set it because if we have 5, but this is the 3-bit counter, the 3-bit counter is going to want to go to 8, right, or 7. So we definitely are going to want to restart it early. So this actually has quite a bit of value, but for our needs, there's really little, very little we would ever get out of it. Yeah, so long story short, we're not going to worry about clearing it, but you could. If you compare this counter to the program counter had an ability to like read data in. You could change its direction where it could count up or count down, a bunch of different things. This is a simpler version of a counter. But it's still that counter, basically an adder and a register, or maybe a JK flip-flop thing, right, that you did an assignment 2. That was assignment 2, right? Yeah. Anyways, all we have is this value, the 4 bits, plus the 2 bits from the counter. We have our 6 bits, and with 6 bits, we saw we could uniquely identify which group of 4 microcode steps we need. One, like each group corresponds to an individual instruction, 16 unique instructions, and which specific step in that microcode or in that instruction, which microcode step do we need? Is this clear? I now have a way to say, okay, give me from this instruction this step. I need the bit patterns for the control signals. These are those control signals, but they're outputs here for our purposes. We're going to observe what they're doing. But we're going to need to connect these outputs to the control signals that we had, those toggles that we had to control, like RAM in, RAM out, all of those things on our system that we were manually doing. We're just going to connect the dots from this to each signal, and so on and so on and so on. There's this one's halt. We haven't talked about the halt control signal yet. We kind of did when we talked about the halt program. We need to deactivate the clock. You'll see how we do this shortly. It's super easy. You could, but we're not, no. Yeah, so we need to go from a mapping of instruction, microcode count, to, well, what's the control signals for that particular situation? This is what we want. Now, the mapping, the actual mapping needs to be put into this lookup table. We have to tell this lookup table, how are we going to actually, like, when you see this input pattern, what does that do? We have to go tell this. Like before, this is a lookup table. I could create a programmable logic array. Like I could build a hardware solution to this problem where we could build a programmable logic array where it takes this input pattern and logically maps it to some other output pattern. We could do this. But as we saw, that grows insanely fast. And it's just too difficult to work with. So we're going to cheese it and use a lookup table. That's all. Remember, the lookup table just maps inputs to outputs. That's all. It's like a dictionary. That's all. Any questions about this? Ask now. All right. So unlike the program counter, this one will count every clock cycle, so we don't need to control when it's enabled. And yeah, this is just the note about we could end early. So lookup table to process instructions. Given the 16 instructions, each with 14 microcode steps, there are a total of 64 rows in the lookup table. Each of these rows corresponds to the bit pattern for the control signals for the row identified by that 6-bit input, the 4 and 2. Okay? Yeah? We could write this lookup table by hand, but that would be a pain in the ass, so we're not gonna. So we're gonna write a script to do it. And the script might look intimidating. It's hilariously simple, and there's a nice design to the script that I think makes it pretty easy to program. And not only easy to program, easy to modify. Like if I were to tell you, go make a new instruction that does something, it should be pretty simple for you to do so based on the script I give you. It's probably what I'm going to have you do an assignment for or something, but I haven't figured it out yet. So similar to the 7-segment display, we're going to write a script to generate the hex file that we can load into the lookup table, just to make our lives easier. With the current configuration of the ESAP system, we have 17 control signals. So we need to map 6 bits to 17. Therefore, a lookup table will have 17-bit output, 6-bit input. Yeah, okay, and each of the output bits corresponds to a specific control signal. Below is a series of constants labeling each of the 17 bits. So, you might say, how is this labeling the bits? Well, there are, so by the way, I don't know if you know this, you can use underscores and numbers to like visually separate groupings of things. Here, a group of 8, and then 1 because, well, 8, 8, 1, 17, right? So, what I'm going to say is, when I have, now you might look at this and be like, that's just a number. Yes, but don't forget that I'm using this number to represent a specific, it really is specifying a specific bit, right? Like, the output table wants to output a 17-bit number, right? Now, I don't really want to output a 17-bit number. I want to output 1 followed by, like if the halt signal is high, it just so happens that if we go here, the most significant bit coming out of this is the halt signal. To be clear, the order of this is just, again, because I wanted a prettier design, right? If you were to build this and you had a different order, it really doesn't matter. All that matters is that this connects to the halt thing, that this one connects to RAM out, this one connects to the ALU, this one connects to the address register, A register in or something, right? That's all that really matters. So the order is not important, but I have set an ordering, so I have to stick with my ordering. And it just so happens that the most significant bit is halt. So all I really care is the bit pattern I want going out is I need the one bit. If I wanted to halt and only halt, I need the one bit from the 17-bit output to be high that connects to the halt part of the circuitry. If I want to do ALU out, I need this bit to be high, right? Now, as far as Python's concerned, like, oh, this is a 17-bit number. That means 128, I guess, right? I got lucky there. That means 128. So Python would store the constant, oh, ALU, that's 128. But the fact that it's 128 isn't really what's important to me. The fact that the bit pattern for 128 gives me the exact 1 bit high that I want that connects. Yeah? Yeah? Hopefully that's clear. Try not to get so focused on like, oh, but that's just a number. Yes, but it's the bit patterns that I care about. Bit patterns here are very important, right? So here's my series of constants. Halt, address register, RAM in, RAM out, instruction register out, instruction register in, output register in, sign, subtract, ALU, B register out, B register in, A register out, A register in, program counter out, program counter enable, program counter in. These, there we go. There we go. Yeah, there we go. 1 bit for each of the 17 control signals would be high. If I want only halt to be high, that's the thing I want to put out. Now we know though that like for load A from RAM, if I were saying like RAM out, like think about what that would mean in terms of the number. If I wanted RAM out, which is, okay, 0001, I have 17. I'm not going to bother drawing. I'm talking about each of these constants corresponds to like one of these things, right? If I were to say like output the constant halt, all I would see is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 for the remaining 16. But we know that several of these microcode steps require multiple bits to be high, right? I need to output maybe, I need RAM out to be high and A register in to be high, right? So I don't want just a single bit high, I want 2 bits high. How can I do that, right? Turns out we know a very simple way to do that. What we'll do is, well, I'll show you. So here the most significant bit, 17, is the halt signal. Halt has yet to be discussed. I'll show you very shortly. Pretty simple stuff. The least significant bit controls the program counter in. The actual order does not matter here, like I already said. The fact that halt's the most significant bit has no real meaning. All that matters is that each signal connects to the correct. Like if you've got a signal that I'm calling halt, here's hoping it halts, right? Here the order is set for the visual clarity that I talked about. So with these constants set, one can easily create microcodes by performing bitwise OR. For example, if I want instruction register out, address register in, I can just OR those numbers together. Take the bit pattern, so IRO and ADR. The bit pattern for IRO is this. The bit pattern for ADR is that. If I OR them together, I get that number. Again, the numbers, I really don't care about the numbers, right? I mean, the thought of doing, I don't know, what is that? 128, 256, 512, 10, 28, 2, 20. This is like 4,000 something. If I say 4,000 or 4, 8, 6, or 32, crap. Okay, that'd be, okay, 1, 2, okay. 1, 2, 4. Let's use a different thing. If I were to say, take the number 8 or 4, and you're like, oh, well, that's clearly that's 12. You're left going like, what? That's stupid, right? Well, why? Well, 1, 0, 0, 0 and 0, 1, 0, 0 equals, like if you OR that, you get 1, 1, 0, 0, right? So it is 12. But we don't usually think about OR on integers because it's kind of weird, which is really not what we're doing. We are doing it as far as Python's concerned, but I'm doing it, it's the bit patterns that I care about, right? So hopefully that's pretty clear. You OR these two integers together, you get another magic integer. It's just the combination of the bit patterns. So this would then translate to, if we outputted it, we'd see 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's what we would get. And that is a microcode step for the second half of fetch, right? No, that's the first part of load A. Yeah, that's the first part of load A, pardon me. From the instruction register into the address register. Yeah? So, each of the 16 instructions will be a collection of up to 4 instructions, 4 microcodes. The first 2 microcodes of every instruction is fetch, whether we like it or not. So each list, basically what we're going to do is we're going to have 16 lists of length 4. Each list of length 4 is the microcode steps for one of the 16 instructions. So what do they look like? Program counter out, address in, RAM out, instruction register in, program counter enable. And then it's no op, nothing, nothing. What? Is there a problem? Yeah. All right. And so I've got a label over there for no op. Load A from RAM. Fetch, instruction register out, address in, RAM out, A in. That's how we're going to generate every single bit pattern. 6 bits come in, and it'll specify something in this matrix, I guess. List of lists. If the bit pattern for the operator is 0001, that corresponds to this list. If we see 00 on the microcode counter, it would be this, 01, 10, 11. That's what we would get. Okay? So what do each of these look like? Well, if we compare what we see here to what we discussed in the previous topic, but with words, we would see an exact mapping, right? How do we do A direct? Instruction register out, A in. B, well, it's the same. These are the same. Save, instruction register out to address, A out, RAM in. Instruction register out, address, B out, RAM in. What's this one? Add, ALU out, A in. If I wanted, think about this. Remember how yesterday we said, or 2 days ago, whatever we had lecture last, yesterday? Yeah. How we'd said we could make A different, where maybe A takes an operand and specifies a RAM address. So what would that look like? Okay, I guess we'd have to say this part would be address in, ALU out, no, address in, then, so instruction register out, address in, then ALU out, RAM in. That's how we would change what that instruction is. let me say that again. I kind of stumbled and I may have messed you up. Ignore this. If I wanted, like, how would I say add, like, let's call it like add B to RAM? I don't know, whatever I'd call it. I don't know. Let's say I created a new instruction that goes into here, 1010, the 10th instruction. Right now it's a no-op, so we can put whatever we want in there. And what I want this to be is an add, but instead of saving the result into A, I want to leave A alone, but save the result to some specific memory address. Okay, so if I said this to like OXF or something, if I wanted, I'm just stylizing what I would have here. This would be 10101111 would be the full 8-bit instruction. What would that turn into? Well, it would be, okay, fetch, instruction register out, address in, clock pulse, ALU out, RAM in. Yeah? That's how I would do it. I would just specify the RAM address. But I could make that instruction. It's not too bad. If I wanted to write a different output where I don't specify a RAM address, but I always just output whatever's in A, because maybe I'm going to have a lot of stuff in A I need to output. So I should write an instruction to do that. What would that look like? Well, fetch, A out, output in. And if it's signed, sign high as well. That's how we would modify and write our own instructions, just by ORing together the control signals we want for that instruction, assuming it fits in 4 cycles. If we needed to take more cycles, by the way, it wouldn't be hard to modify this. The original version, by the way, of my instruction set I had was actually going to require 5 microcode steps. So I needed to have it end early. I had a counter, and if it ever got to 5, it would reset it. So it would only ever go 0, 1, 2, 3, 4. And whenever it got to 4, it would reset itself, but it would do the 4th thing, so we needed 5 microcode steps. So there's an old version, you can find it on GitHub, an old version of this, where this was a list of 16 by 5. And I had additional things we could do to have slightly more sophisticated instructions. But I got rid of that to simplify the design. And it's better this way, I think. But yeah, we could make this pretty easily. With not too much pain and suffering, we could make more sophisticated instructions that require more microcode steps. But here we only are using 4. So we OR them together. So, okay, notice that each of the 16 instructions start with the same 2. No matter what we're doing, no matter which instruction we're running, we got to fetch it. Now, what's kind of neat is, let's say for, like, here's just like food for thought. Consider that, like, what must be happening in this system design? Let's say the first instruction I have in my computer is this, right? So load into A the value stored in register F, or in address F, okay? Right? Consider that, I mean, really, when you turn the system on for the first time, in digital, there is a value that will be in the instruction register. Okay? And in digital, the value that it'll be when you turn it on always starts at 0. Now, the same interesting phenomenon, to a more interesting effect, would happen if this wasn't within digital, but if I took my circuit that I have in my lab, in my office, and turned it on, there would be a value in the instruction register. But does anyone know what that value is the moment I turn it on, physically, on a chip that I have? The answer is no. You don't know. I know I know there'll be like 4 bits there for that specify an instruction. Really, there'll be 8 bits. It's 8 bits wide. But in terms of decoding an instruction, I only really care about this. Whatever is in that instruction register, I don't actually know what instruction is in the instruction register, right? So before this, like think, I need to put this instruction into the instruction register. I need to fetch it. But the fetch is the first two steps of this instruction, which is not in the instruction register. So how can I fetch an instruction where the first two parts of the instruction is fetched before I've fetched it? Does the problem make sense? Do I have a picture of the whole system? Right? Spoiler, it goes down there. Okay, there is an instruction. I turn on the system, there's an instruction in here. I don't know what it is. Right? We don't know what it is. The problem is, I need to get the instruction from RAM. I need to get this instruction from RAM. Okay? But the fetch part of the instruction of this, because we know the first two steps of this is fetch. So I need to get the instruction from RAM without having this instruction's first two clock cycles available to me, because I actually have XXXX in the instruction register. X is meaning I don't know. Is this clear? It doesn't. Because no matter what instruction is in there, no matter what bit pattern I have in the instruction register, no matter what the 4 bits are to specify which of these 16 we have here, no matter what it is, we do fetch. Meaning, the fetch for the instruction that we're about to perform, the fetch part actually came from the previous instruction in the instruction register. Do you see what I mean? Really, like, okay, let's say the next thing I do is load something into B, right, which is 0, 0, 1, 1, and I load 1, 1, 1, 0, the value in that one, right? Consider that, okay, this value is in the instruction register. We move this into the address register, then RAM to A. Now we need to go to here, right? The value, okay, we are program counter, okay, we are starting the fetch of this instruction. But the fetch that we're actually running for this instruction is actually this instruction's fetch. It's the exact same fetch. But the point is, the value in the instruction register, even though this is the next instruction I'm supposed to run, the first two parts are actually coming from this instruction's fetch part. Which I think is kind of neat. It doesn't matter based on exactly what you said. The fetch is the same no matter what we're doing. It doesn't matter which instruction's in there. Basically, if I showed you these two parts, and said which instruction did this come from, you wouldn't know. It doesn't matter. It's the same. So basically what I'm saying is, if I ran in digital, when I hit run, if this is the first instruction, this is the second instruction. In digital, I turn it on. I don't have a case of X, 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 X. I actually have a case of 0, 0, 0, 0. I know that that's what's going to be in the instruction register because digital starts everything at 0, which is nice. So I actually have a no-op in fetch. So we actually run this part of the fetch, this part of the fetch, but now this instruction's in there. Then we run this part of this instruction, then this. Then the next thing we're going to do is try to run this instruction here. But really, we go back and run this instruction's first part of the fetch, this part of the fetch. Then we go down to here, down to here. So there's actually, I kind of lied to you. The same bit patterns are going to be run, but like where and when things are referencing the correct instructions, things, there's a little bit of a quirk to it. Raise your hand if this is clear. Raise your hand if this is not clear. It's not clear?
Yeah.
It's not clear. Okay, what are you wondering?
So you're saying that it's not going to run line by line, it's not in order, right?
So let's just start again. I turn on the system. Okay, we all know the first thing you have to do to run any instruction is fetch it, right? So if I want to run this instruction first, we want to run these 4 things right here, right? Do you agree? That's what we want to happen. But in reality, pay attention. If this hasn't been clear to you, pay very special attention to what I'm saying. In reality, that's not what's going to happen. Because in digital, when I turn it on, I have 0, 0, 0, 0, 0, 0 in the instruction register. Now I only care about the 4 bits for the operator, and that's no op. So really what's going to happen is what's in the instruction register currently? 0, 0, 0. So we run 0, 0, 0, microcode counter 0, increment the microcode, no ops, 0, 0, 0, then microcode counter 1. Now the contents of the instruction register become 0, 0, 0, 1. After running that part of fetch, because we just put it into the instruction register. So now, after step 0, after step 1, now we actually have the instruction we want to run in the instruction register. That means we then run 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, where the counter is 1, 1. The following instruction is this one. 0, 0, 1, 1, 0, 0, 1, 1 corresponds to load into B from RAM. So I want to run this line, but I'm not going to. Because what's in the instruction register currently? 0, 0, 0, 1. So we run this instructions fetch. Now the instruction register actually updates to be this value, because now we put the new instruction into the instruction register. Now we can go and run this and then this. So the fetch part and the actual steps that we're doing to perform the instruction really are kind of independent. I could have designed this in another way. Maybe what I should have done is made it so each instruction here really was 2 steps, and I completely eliminated the fetch from the lookup table and built like a programmable logic array, which would have been really easy for fetch in hardware for the first 2 steps. Like, I could have redesigned it. At the end of the day, the point is it doesn't matter what the instruction is until we get to this part, because otherwise the fetch is it's the same no matter what. Did that answer your question?
Yeah.
Are you sure? Mostly?
I was asking about how it ran.
Okay, and then the step by step. When in doubt, like everything when you're learning to program, when in doubt, what does it say? Now, I realize when it's in Python and you're like, what does the code say? It's right there. Now when I'm saying what does it say, there's a bit of a like, well, what's the code saying? And what does the physical layout mean? Like, there's a little bit more to it. But when in doubt, you could figure this out, right? You just got to take your time. Any last questions before we wrap up? All right, cool. We'll pick up here Tuesday.
Magic rocks.
It is. You make them think.